do it like, put it along the z direction, then you get 1 plus sigma 3, and everybody knows that's with 1/2. That's precisely the matrix 1, 0, 0, 0. So it tells you that if this is in the z direction, that 100% is polarized along the z direction. And then you put that matrix row in here, and etc. So you get this spin thing. Now, why would you be able to use this for phi's? Because for phi's, we will use it in the same way. And that is because phi also has these initial state protons on the outside, and we have with the polarization. I mean, it is an initial state, it's a proton state. So we can, in the same way, if we have states, we could use here explicit spin alpha indices, but then the correlator would be a 2 by 2 matrix in spin space. But rather than a 2 by 2 matrix, we use this sort of density matrix formalism to not use a matrix, but use a vector which signals what the matrix is. But then it is a density 2 by 2 matrix which is sandwiched between the spin states of the psi 0 to x or whatever. That you always have to remember if you work with it explicitly. Now, this vector you can easily check that this s squared is smaller or equal to 1, and that this means that SL squared plus ST squared has to be smaller or equal to 1, and SL is called if you want longitudinal spin. In the rest frame, it would be, in the rest frame, essentially, this would also be proportional to the mass. This thing would be just the spin along the z direction, and in a fast-moving nucleon, this is essentially proportional to the momentum, and it is essentially what is called helicity. So that's all that is about this spin vector. Now, having this, you can have not only p slash, but you can have p slash gamma 5, and you can have p slash gamma 5 and then an st slash. Of course, SL only can appear as a number because p slash we already had. So that's our spin and that spin. And I mean, you can vary these things. You can, an experimentalist can choose if he or she makes SL large or ST large or both of them 0 unpolarized. Now choose, try to figure out in a hard way how to polarize things. But things can be polarized. Okay, so that's the thing. Now, what is the meaning of these functions? So I hope you believe that you have more freedom as soon as you have more vectors. That's what is in here. So as soon as you have SL, you also have p slash gamma 5. And if you have ST, you have p slash gamma 5 ST slash. These are allowed Dirac structures. Parity and the rest is also fine. So these are allowed. What is the meaning of F1? As I said, F1 is essentially you go then to, you do your integration and you see that it has to do with the number of fermions, number minus antinumbers. What is this thing? It has an additional gamma 5. Now suppose that here was 1 plus or minus gamma 5 in an original UU bar. What would you say if you have 1 plus gamma 5? You say, I have purely right-handed quarks, right-handed fermions. And with minus 5, you would have left-handed fermions. So G, or delta Q short, in short, this is also called, this is Q of x, this is delta Q of x, capital delta Q of x, the polarized PDF. That PDF essentially is, because of the gamma 5, it tells you the number of right-handed minus number of left-handed quarks, or the other way around. I mean, let's forget about signs. What is this thing? This function, H1, also called delta curly Q of x, transversity also. What is it? Now, this H, look at its structure. It has a gamma along the proton, so that's a gamma plus or minus, a strong, and then it has a gamma transverse, because ST is the transverse component, a gamma T. Now that tells you, oh, the only way where in this expression, which is the standard projection operator for fermions from your textbook in the Dirac chapter, it tells you that if I want a transverse gamma matrix, it must be sitting here, S. And S is then the spin vector for a single fermion. So this tells you that if this is transverse, that you have transversely polarized quarks. So 8 is transversely polarized quarks. But it can only appear in the parameterization if you also have an ST, which means if the target is also transversely polarized. So these are transversely polarized fermions in a transversely polarized target. That's what they represent. And then you can see that if you have the right factors of x and 2 pi and I don't know what, that these things are nicely normalized to numbers of transversely polarized quarks minus the number of oppositely polarized quarks. So this is how you read it off in essence. Now there's more. So this is how you read off what each of these is. These are unpolarized quarks, these are chiral quarks, right-handed minus left-handed, and these are transversely polarized quarks in a transversely polarized nucleon. And chiral quarks only can occur in a longitudinally polarized target. So if this would be all. But in this expression, the PT slash has not been used. The transverse momentum of the quark has not been used. If you allow for the transverse momentum of the quark, something else can happen. Oh, yeah, you can get a pt.st structure. pt.st is something which now can occur. P.s cannot, okay, this can pop up. P slash gamma 5. Now, how many gamma matrices are there? Only here is a gamma matrix. So this thing must be gamma 5. So it must be a chiral quark. Okay, so this thing represents chiral quarks. But in my expression, I only see that this thing happens when ST is unequal to 0. So this function represents chiral quarks in a transversely polarized nucleon. So that's the first extra that you gain when you have PT available. You can find chiral quarks in transversely polarized, which you couldn't find if you don't have PT, and you also can find transversely polarized quarks in a longitudinally polarized nucleon. That you will believe that. Actually, that's where the name of the functions comes from. Functions G are always chiral distributions. F are unpolarized quark distributions, and the H is equal to transversely polarized quarks. So what would be the name? This is the name of chiral quarks in a transversely polarized target. So what would be the name of the function which represents transversely polarized quarks in a longitudinally polarized target? Now, transversely polarized quarks, there we used H as name, so it's H. It's called H1 because everything goes with this capital P, so it's leading. So it would be H1, but then in a longitudinally polarized target, so it would be H1L. So here you would have G1L and H1T, and then with PT you have G1T and H1L. In the full expression you will see an H1L popping up. So that's the two additional ones that you can have. All of these are spin-spin correlators, spin-spin correlations. You always have polarized quarks in a polarized target, unpolarized quarks in an unpolarized target. Now, if you allow for T-odd stuff, you get something in addition. You also have things of the form PT slash PT. Oh, this is a transverse gamma matrix. Transverse gamma matrix, remember again this structure, can only be something which is sitting here. So that's this must be a transversely polarized quarks. That you see from the Dirac structure. But in this whole expression there is no SL, no ST. It's in an unpolarized nucleon. So this function represents transversely polarized quarks in an unpolarized nucleon. It can exist because PT is available. And you have, similarly, you have the possibility that with just a P slash you have PT cross ST. Actually you need a cross, but that's parity constraint. Not PT dot ST, but PT cross ST, which is a number. I mean, this is two-dimensional space, and then the outer product is also a number. So that's, I mean, this is not suddenly a vector. Yeah. So that's this. So you need PT. You look at the structure. It just has a gamma matrix, so it's unpolarized quarks. That's why the name is an F. But you need an ST, and so it is only occurring in transversely polarized nucleons. So these are unpolarized quarks in a transversely polarized nucleon. And this is how the naming works. And so these are two functions, and both of these functions have the property that they are T-odd. So both of these functions, if you would now say, I need the phi with a gauge length plus in one process and minus in another process, then the process where you need phi minus, both of these, this whole thing will change sign. Okay, so that's this thing. And so these are, if you want, spin orbit or spin momentum correlations. And that's typically why people talk about spin orbit correlations in a nucleon. For that you need these TMDs. Although this is not pure, this is of course not spin orbit in the sense of L dot S. Be careful. People often say we can measure orbital angular momentum in a nucleon using TMDs. That's impossible, let me tell you. Impossible in a direct way. I mean, if there would be no orbital angular momentum, there would be only spherical PT dependence, and all of these things wouldn't exist. So you can make a statement, if you see TMDs, it looks like there should be orbital angular momentum somewhere in the proton, but you don't, there's no sum rule which immediately tells you how large this thing is. While these spin sum rules, this G1L, if you integrate that over X, you really have the quark spin parallel or anti-parallel to your proton helicity, and you measure that. And so you really measure, you have these spin sum rules, but not orbital angular momentum sum rules, not directly, indirectly. You need GPDs to do it. Okay, so definitely that is the, there is new information, and there are correlations, single spin correlations, which only have either the target polarized or have the spin, the quarks polarized, and not the object they came from. So they are single spin objects, which in QCD seem hard to make. But I mean, the nucleon is a non-perturbative object, and I mean, you have mass, and I mean, there they can exist. And now immediately you may have one other thing, yeah, but in the hard part they may not exist. And that's indeed true. And that's actually with more often chiral quarks exist, but transversely polarized quarks, for those who know a little bit about spin physics, transversely polarized quarks are essentially, I mean, they are spin half objects. You know, a spin along the x direction is of course, what is it? 1 over square root 2 along the z direction, plus or minus 1 over the state along the minus z direction. And what you see is that the diagonal thing in transverse spin for the quarks is off-diagonal in helicity or in chirality. And of course, you know that off-dimensionality and chirality cannot exist, so that if you have some process like CITES, in which these functions which have the name H, occur, that they must be balanced. In the hard process, you don't have chiral transitions. I mean, then you would need mass terms. Yeah, okay, if you have charmed quarks floating around, yes, then you can do it. But not if you have only light quarks. So then the hard part can change chirality, and then chirality changes in the lower block, and so you better also change it in the upper block. And then things can still work out. So this is why chirality distributions like H1 or H1 perp, it doesn't matter if it are T-odd, as soon as the name is H, you need another function in your final cross-section expression which has also an H in there. So you need transversely polarized quarks in both things, in fragmentation and distribution. This is sort of chirality, this chirality filter that you have. And that's why why it was so hard to measure transversely polarized quarks, because you can't do it in deep inelastic scattering, because then you only have one soft piece. You need a second soft piece to say, transversely polarized quarks, that they can also go into hadrons through the same mechanism. Okay, so that's why H functions only appear in pairs. For gluons, you can do the same sort of thing. Let me immediately tell you that without going too. Gluons essentially don't have Dirac indices, but they of course have Lorentz indices, mu and nu. I want a mu and a nu. I want to describe these gluons, and I want to parameterize them. I use the same sort of constraints. I need the expression. The expression has F mu nu's in it. I won't dwell on that because it takes too much time, but I'm going to compare it with what you would do for gluons if you didn't know better but had gluons in your initial final state. You would say I have an epsilon epsilon, and that's a transverse GT mu nu. This is essentially, there's only two polarizations for an outgoing physical spin one particle, or no, not spin one particle, for gluon, for massless gauge boson. So this summation gives you just a transverse mu nu. Now the GT mu nu, because the longitudinal part is defined by the momentum. So GT mu nu. Okay, now that's one way that you can parameterize this soft piece with indices mu nu. No Dirac indices, but now Lorentz indices. So it could be a G mu nu. Of course, it could also be an epsilon mu nu, but an epsilon mu nu signals, you need that if you select. If you don't sum over, so then you need lambda, you need the polarization, and then you have this. So that's again appears together with an SL, so you need a longitudinally polarized target, and then your gluons can also be polarized. And with PT you can get one additional structure, which is symmetric in this thing, which you can make it traceless, etc. And it also induces a new function. And now again, you have to compare with this and that, and then this thing is unpolarized, and this thing is polarized, but it's circularly polarized. Only two circularly polarized, the difference of two circularly polarized gauge bosons gives you an epsilon tensor. That I should give that as an exercise. You know your epsilon plus and minus, you know these matrices. Look at it and put them in this 1, 2, so that's only a two-dimensional space, and see that you get the off-diagonal antisymmetric thing, which is not a symmetric thing. Then you get your G mu nu, your epsilon, that you get it when you take the difference of two, of plus circularly and minus circularly, so the left and right circularly polarized gluons. Now, this thing, put here px or py, and then what you see is essentially that if the momentum of the gluon is along the x direction, you have purely, then this thing projects out the y direction, and the other way around, or the x direction. I forgot which one. But at least there is a coupling between the momentum of the gluon and the polarization. And this represents longitudinally polarized gluons. So just from the structure, again, by comparing what you know from your textbook, you get these functions represent unpolarized gluons in an unpolarized nucleon. There's no S factor. Here there's a longitudinal, so these are in longitudinally polarized nucleons. It's an epsilon structure, which tells you it's circularly polarized. This is this structure tells you that it's linearly polarized. You have to think about that a little bit, yeah. And then there is, let me see, there's nothing else, so it's unpolarized nucleons. So you can have linearly polarized gluons in an unpolarized nucleon. This is recently, this is used in saying this may have consequences at LHC. You may use the fact that you have PT dependence coupled to the polarization of gluons to sort of produce longitudinally, linearly polarized gluons. I mean, in glue scattering, sometimes these gluons are linearly polarized. How would you detect it? Yeah, it's coupled to PT. So you need to do something in your final state. You have to measure this sort of QT dependence. So you have to measure in the simplest way that you could do it is, you say the two gluons come in and you have to measure the PT, the QT sort of, just like in Drell-Yen. The photon has a transverse momentum with respect to the two beams. Now the Higgs has a transverse momentum with respect to the two beams. But all of these functions with PT, these are the functions which are there in the usual collinear treatment. This function, because of its structure, will simply disappear if you integrate over PT. I mean, this is a tensor, a second rank tensor, but if you integrate over PT, this will disappear. So that tells you that if you don't measure any PT dependence, you will never measure this sort of thing. So you have to measure PT dependence. Now the problem is that if you want to see what is happening at large PT, now you say, but that's fine. Sometimes the Higgs comes out with large PT. But large PT is generated from small PT, if you want, by radiation of gluons. And this function never will produce this function through radiation. So really such a function, if relevant, would only be relevant in the region where the Higgs or the whole Higgs sector, wherever it decays, if you look at the PT of that sector for modest PTs, a GeV or so, or a few GeV, which seems in an environment of course TeVs, an extremely hard job to do, to measure to such a precision. Moreover, nobody knows how large these functions are. But these functions in principle could be large. I mean, these are new functions. Nobody tells you that these functions should be just 1% of the F1. I mean, they could be 10 times as big as F1. I mean, there are constraints on these functions. They cannot be, I mean, like spin. Of course, if you look at polarized quarks minus polarized quarks along a direction minus the quarks in the opposite direction, you can never get more than F1 itself. I mean, that's when it's 100% in one direction or the other. So, of course, for all these sort of polarized functions, there are, bounds that you can put. And for these polarized things, you can all sorts of bounds, Sofort bounds, known in the literature, etc. So you can have bounds on these functions. So this function naturally can never be larger since it's a polarized function than this one. But that doesn't mean that it cannot be 60% or 70% of it. But then nucleons or quarks in a nucleon would be really transversely polarized, linearly polarized to gluons, which is not very natural in that sense. So most likely the function is not that large. At least I wouldn't know a mechanism that naturally produces it in models.
Sorry, the dimension of second term in parentheses. Is it something?
Oh, this would be PT squared. Sorry, that would be nothing new. The new indices are here. This is simply the trace of this term, so it's traceless. Yes. Yeah. Sorry. Yeah. Very good. Is it everywhere? Yeah, it's new also here. Because I noticed that some indices sometimes have changed. Okay, so you can with this 1 plus or minus gamma 5, you can play with it and then you get these pictures that people produce, unpolarized quarks and so. You showed yesterday those pictures in up and down quarks. You can make matrix representations in spin space so that you take right-handed quarks in a polarized nucleon, right-handed in an oppositely polarized nucleon, left-handed, and then you look at what is, and then these are the densities, and these are the off-diagonal densities, H1. And if you take here not right and left-handed quark, but transversely polarized quark, this jumps to the diagonal, and G becomes off-diagonal or whatever. And the nice thing is, here there are only few functions. As soon as you put these other functions in, all these other functions, which have a natural interpretation, you see, as I said, F's unpolarized quarks, G's polarized quarks, and 8 transversely polarized quarks, and then you have some functions that are the red ones need PT. The normal thing, there are 3 of these distributions, and 2 of these are T-odd, and these are these strange functions which are transversely polarized quarks in an unpolarized target, so that's sort of this structure. And this is the other T-odd, which is unpolarized quarks in a polarized nucleon, but then in a longitudinally polarized nucleon. And as I said, you not only have G1T, which I showed, but also H1L, which is longitude. These are these spin-spin correlations, as said. So these are the sort of the 8 different structures that appear if you allow PT. So that's then you get a richer structure. So now let's get to the problems. And an idea of how we solve them. Okay, so these were the basic objects. This was the basic object. This is a priori something you should simply take along. So you would say at first sight, this destroys my nice box description of this hard process. Because I have additional gluons, and this gluon can couple anywhere in the hard process, or in the final state, or wherever. So multi-parton correlators you need, we can write them down. In principle, they're just matrix elements. Okay. Now, turns out that some of them are really needed, because the original expression that I have here, let me go back, I should use this thing, that's easier. Let me go back here. This thing only had 0 psi, so this was not gauge invariant by itself. Now the nice thing turns out that some of these gluons precisely produce you the object, which I outlined already yesterday, is what you need. You need some connector between point 0 and psi, and it's a part-ordered exponential, so you need these gluon fields to produce you a gauge invariant object. Okay, but transversely polarized gluons generally don't show up. I mean, they show up in the parameterization, but they become suppressed, and that's actually what is precisely happening. Let me skip this. You do the calculation, and you see that these gluons with longitudinal polarization in a Drell-Yen situation produce you these 2 gauge lengths going to -infinity and back. Well, if you do the same thing in an environment in which the color goes into the final state, because it's just the initial and final state color flow effect which causes this, it comes actually from the prescription of this propagator after you couple the gluon, or this propagator, which differs with plus or minus I epsilon, and then you get theta functions, etc. in your calculation, and that shows how the paths run in these. If you do not only one gluon, but of course this represents the absorption of all gluons. Okay, you get these 2 gauge lengths. So you see, ultimately they build up a phi minus to be used if I describe the correlation. So if I describe how these quarks are sitting in a nucleon, I need a phi minus. And in this process, if I have absorbed all these gluons, I come to the conclusion that as far as the quarks here are concerned, that I need a phi plus. And this tells me that in the sort of handback calculation of Sidis, I need phi plus, and in the handback calculation of Drell-Yen, I need phi minus. Which tells me that if I put in then the parameterization, that if you forgot about the plus minus, you will get an unexpected minus sign in the asymmetries, and if you take it into account, you explain this, the switch of sign, which still has to be firmly established. So let's wait for that. And actually, yeah, this and that are time reversed situations. So that's why you know how the functions H1 perp, in this case, appear with plus or minus signs in the 2 processes. This is the technical way. You have to do all this calculation. You have to expand the A field in the collinear piece, the transverse pieces. The transverse pieces don't matter except the transverse